Modular arithmetic. When a is equal to mq plus r, where q is the quotient and r is the remainder upon dividing a by m, we write that a mod m is equal to r. That is, a mod m means the remainder when a is divided by m. For example, 13 mod 5 is 3, because when you divide 13 by 5, you get quotient 2 and remainder 3. Now we'll define the relation in the set of all integers. Given a positive integer m and integers a and b, we say that a is congruent to b mod m if a and b have the same remainder when divided by m. For example, 33 is congruent to 18 mod 5 because both numbers, when divided by 5, give remainder of 3. And 12 and 17 are congruent mod 5 because the remainder of 12 mod 5 is 2 and the remainder of 17 mod 5 is also 2. It turns out that congruencies like this have some properties similar to properties of equalities. You know that we can add, subtract, and multiply equalities. It turns out that we can do the same with congruencies mod when the modulus is the same. Like here, the modulus is 5. We can add them, add the left-hand sides, the right-hand sides, write the same modulus. Because these are true, the result is a true congruence. You can check add here, and verify that the remainders are the same. Subtract from 33, 12, and from 18, 17. You'll get another true congruence. Or you can multiply the left-hand sides, the right-hand sides, write the same modulus. Now verify that this is also true. It turns out that this is true in general. If m is a positive integer and you have two congruencies, two given congruencies, mod m, you can add them, subtract them, multiply them. The result is again a true congruence. From here, we obtain the next theorem. In the previous theorem, select C and D to be C to be A and D to be B. When you multiply them, you'll get A squared, B squared here. That is, from one congruence that is true, we can write a new congruence that is true simply by squaring both sides. If you multiply these two now, using the previous theorem, you'll get this. If you multiply this and this, you'll get A to the 4 congruent to B to the 4 mod m. So we can multiply, we can raise both sides of this congruence, that is A and B, to the same power. You'll get a true congruence as long as that power is a positive integer, like here. Problem. compute 6 to the power 1001 mod 7 and 8 to the power 402 mod 5. First, we start with 6. We can write that 6 is congruent to -1 mod 7. How we get this? If you subtract 7, basically is 0 mod 7. So if you subtract 7 from 6, you'll get a number congruent to 6. Another way to check this is apply the definition. The remainder of 6 is 6, and the remainder of -1 mod 7 is also 6. So this is true. Now, we want this power. First we'll square. Because this is true, 6 squared will be congruent to -1 square mod 7. But -1 squared is 1. I can replace it here. I'll keep 6 squared like this. I will not write 36. Now I have to approach this number from below. 1001 is not even, so I cannot raise this to some power to get this, because I can raise only to positive integer powers. But I can raise this to the power 500 to get 6 squared to the power 500 to get here 1000. Exponent 1000. 1 to the power 500 mod 7. So this means that six to the power 1000 is congruent to, this is just 1, mod 7. And finally, 6 is congruent to 6. Multiply 6 is congruent to 6 mod 7. And this, and you'll get 6 to the power 1001 is congruent to 6 mod 7. For the second number, we have to start from this. 8 is congruent to subtract 5 from 8, you will get 3. 8 is congruent to 3 mod 5. Yeah, this is true. Then raise both sides to the second power. 8 squared will be congruent to 3 squared mod 5. But 3 squared is 9. So this is 8 squared is 9 mod 7. Oh, sorry, mod 5. 9 is congruent to -1 mod 5. Yeah, the remainder of 9 is 4. The remainder of -1 is also 4 mod 5. So they are congruent. Now, transitivity property holds. This is congruent to this is congruent to this. So the first is congruent to the 2. So we get 8 squared congruent to -1 mod 5. -1 is good because we can compute easily any power of -1. Here I need 402. It is even. Divide this by 2. 402 divided by 2 is 201. So raise both sides of this to the power 201. As we know, the result is a true congruence because the congruence from this congruence is true. Now, the left-hand side is just what I need. Here, I need 8 to the power 402. 2 times 201 is 402. And this is just -1. So this is -1 mod 5. And because -1 has remainder 4, it is 4 mod 5. We can replace -1 here by 4 by transitivity. This way, we'll have a positive number, but -1 can stay. It is still correct. Okay. The next example is about the United States Postal Service's money order. Those have identification number consisting of 10 digits together with an extra digit called a check. The check digit is the 10-digit number modulo 5, modulo 9. The 10-digit number modulo 9. For example, this 10-digit number has check digit 2 because if you take this number mod 9, you'll get 2. So the check number is 2. We write that 2 at the end. And this is the identification number. Together with the last digit. And this helps to catch some errors. For example, if this number were incorrectly entered into a computer as say this, you see here there's some difference. The correct digit is 8 and it was entered as 7. And the check digit now take the first 10 digits, mod 9. The result is 1. And because here we have a 2, it is clear that there is an error somewhere. So how you check that this mod 9 is 1? You simply put put this in the calculator. 39, 53, 97, 81, 64 divided by 9. The result is so the result is 439330907, and then we have some ones. So the quotient upon dividing by 9 is the floor of this number, which is the integer part here, and the remainder will be the difference between the original number, the numerator here, and this number times 9. So I put this in the calculator. 39, 53, 97, 81, 64 minus 43, 93, 30, 907 times 9. And the result is 1. So this way we compute that is the usual way we compute the modulus. If your calculator has a mod function, then you can use it. Otherwise, you use the division as we know.